Okay, there are certain aspects of matrix that we have already seen, but now what we are going to do is give proper names to that. Plus, in addition to that, we will look at what is adjoint. Okay, so let's actually take a matrix 1 3 1 2 1 0 and 0 2 minus 1. Okay, you have to take a square matrix. The first is minor. What does minor mean? Now here what it means is, if you take an element, say A11, its minor is going to be the determinant of the matrix that is left when the first row and the first column is deleted. So if you delete the first row and the first column, you are left with 1 0 2 minus 1, which is equal to minus 1 plus 0, which is minus 1. Similarly, minor is determinant of, if we remove the first row and the second column. So first row, second column is removed, means 2 minus 2 0 0 minus 1 is left. Its determinant would be minus 2. Plus, actually it would be wrong to say plus 0, it should be minus 2 minus 0. So minus 2. Similarly, A13's minor is first row and the third column is removed. So 2 1 0 2. Its determinant will be 4 minus 0, which is 4. A14's minor is, sorry, there is no 1 4 here. It has to be 2 1. The second row and first column is removed. So you are left with 3 1 2 minus 1. 3 1 2 minus 1. So 3 times minus 1 is minus 3 minus 2, which is minus 5. A22's minor is so second row, second column has to be removed. 1 1 0 minus 1, which is minus 1 minus 0. A23's so second row, third column. So 1 3 0 2. 2 minus 0, which is 2. A31's minor is 1 3 1. Third row, the first column. So 3 1 1 0. So 3 minus 1, which is 3 times 0 is 0. Minus 1 is minus 1. A32's minor is, now third row, second column is removed. Third row, second column. So 2 1 1 1 2 0. Third row, second column. 1 1 2 0. 1 1 2 0, which is equal to 0 minus 2, which is minus 2. A33's minor is 1 3 2 1. One minus 6, which is minus 5. Verify this, because here, since you tend to make since you have to do same steps multiple times, the chance of making a mistake is high. So keep verifying at every step. Okay, so that is the minor. Next is cofactor. Now again, cofactor of the cofactor is there for every element. So cofactor of A11 is minus 1 to the power of 1 plus 1. Row number plus column number. See, again, we have done this before. The only thing is now we are talking of a particular name for it. Cofactor. So minus 1 square, which is plus 1. Actually, we are not interested in 1 as such, because anyhow we are going to use it for multiplication. So 1 doesn't have an impact. So what we are more interested in the sign itself. 1, 2 is equal to minus 1, 1 plus 2, minus 1 cube, which is minus A13, 1 plus 3 equal to minus 1, 4, which is plus. Similarly, 2, 1, minus 1, 2 plus 1 equal to minus 1 cube, which is minus 1, but we are interested in only minus. 2, 2, so if it is an odd number in the exponent, we get a negative sign. If it is even, we get a positive. 3 plus 1 is 4. So even this will be plus. 3, 2. This is 3 plus 2, 5, which is odd, negative. 3, 3 is equal to minus 1. 6 equal to plus. Okay, so if we have to write it in the matrix form, it will be like this: minus, plus, minus, plus, minus, plus, minus, plus. If it is a 2 by 2 matrix, it will be plus, minus. This is second row, first column. So odd. So minus, plus. So now adjoint would be what? Adjoint of A. Shortly it is written as adjoint A. This is equal to, now write down all the cofactors and the minors. Okay, so cofactors is nothing but the sign plus or minus, and minor is the determinant, minus 1. Let's actually write it and then close the matrix. Plus minus 1 minus minus 2 plus 4 minus minus 5 plus minus 1 minus 2 plus minus 1 minus minus 2 plus minus 5, and its transpose. Yes, so adjoint of A is equal to the transpose of the matrix made up of the cofactor and the minors of the elements of matrix A. Okay, so let's simplify this. Minus 1, 2, 4, minus 1, minus 2, minus 1, plus 2, minus 5, and its transpose. So now let's find the transpose. Nothing great, just convert the rows into columns or columns into rows. So minus 1, 2, 4, 5, minus 1, minus 2, minus 1, 2, minus 5. So this is called the adjoint of A. In case of a 2 by 2 matrix, right, let's say B is equal to A, B, C, D. So adjoint of B would be, you can follow all the steps, or what you can do is take the shortcut, right? Just exchange the principal diagonal. So if you exchange it, what happens? This becomes D, this becomes A. And take the negatives of the other two. So minus B, minus C. Now, another very important aspect that we need to know is whether a matrix is singular or non-singular. Now, if the determinant of a matrix is equal to 0, then it is called singular. If the determinant is not equal to 0, then it is non-singular. Inverse of a matrix. Now, what's an inverse? Remember division? We have looked at addition of matrices, subtraction, multiplication. What about division? Say, for example, you want to 3 by 2 divided by 6 by 4, let's say. Or not 6 by 4. Let's say divided by 3 by 2 itself. You want to. Now, if you directly try to do division, it's going to be a little bit complicated. But what do? We take the reciprocal of this and convert the division into a multiplication. So multiplied by 2 by 3. So now it becomes simple. We just simplify and then we write the answer. But here we don't call it as a reciprocal, we call it as a inverse. We convert the division of a matrix into multiplication using the inverse matrix. Yes. Now remember, A, B equal to BA. Remember, the multiplication of matrices is not commutative, but a matrix may multiply with another matrix in such a way that it is commutative, and when you multiply it, it gives you a identity matrix. Yes. So here what happens is AB equal to BA equal to I. In this case, B is called the inverse of A. And the way we write it is A, if this is the matrix, the inverse is A minus 1. Yes. So purely based on this, we say A times A inverse is equal to A inverse times A is equal to I. Now, using the adjoints, we can prove that A times adjoint of A is equal to adjoint of A times A is equal to determinant of A times I. Yes, now adjoint of A, what we'll do is we will take this to the other side. So A times 1 by A times 1 by determinant of A adjoint of A is equal to 1 by determinant of A times adjoint of A which is equal to I gets left out on the right hand side itself. Now because determinant of A is in the denominator, it means that this can't be equal to 0, right? Now if you compare this with this, what this means, because the right hand sides are, remember, identity matrix, so that means left hand side should also be equal. That means this is equal to this is equal to this. So basically what it means is A inverse is equal to A times 1 by determinant of A times adjoint of A. Now this can be written as, so what this means is that A inverse is equal to 1 by determinant of A times adjoint of, and of course this is possible only if the determinant is not equal to 0. So that is a formula for finding the inverse of a matrix, and there will be an inverse only if the determinant of the matrix is not equal to 0. So we have seen what is minor of an element, we have seen what is cofactor, we have seen what is an adjoint of a matrix, we have seen what is singular and non-singular matrix, and we have seen what is inverse of a matrix. Okay, before we close, a slight elaboration to avoid any confusion. Here we have seen what the minor is. So the cofactor of an element would be the sign and the minor. So cofactor of ij would be equal to -1 I plus j times the minor of aij. We have already calculated the minor previously. These ones we have found out the signs. Now the product of these two would give you the cofactors, right? So all these are the cofactors. Okay, just wanted to clarify that. Apart from this, there are other ways of finding the inverse. We will look at it in future sessions. That's it for today. Bye for now.